Welcome back to the shop. Oh, I had just positioned the cat camera, but now he's coming back over here. Well, I think he's going to do the thing where he orbits around the camera for a bit and doesn't settle down, so maybe I'll, won't worry about that for a bit. So, yeah, welcome back. This will be an extension, well, a continuation of the kind of PLC voltage glitching project we've been doing for a little while. Let's get this focused on something other than whatever that is. Oh, geez. That didn't sound good. I'm gonna have to take this arm apart again. Oh, man. Okay. Here's our current victim setup. Oh, will that stay? I think it will. Oh wow, Tuco's like climbing around behind the curtains, I think. Okay, so I have some good news and some bad news. I guess it's mostly bad news, but well, it's interesting actually. So I've been making some progress on glitching this. Oh, Tuco, what the hell are you doing? He's between the curtains and the wall, and I think he's trying to maneuver the curtains around. Do you want me to help you with that, cat? I don't even know where he is. Oh. Alright, cat. Silly critter. Alright, well, so my goal with this has been to inflict a little electrical glitch, so momentarily pulling its core voltage, the 1.8 volts that runs the processor. So very quickly pulling that down to ground and then letting it oscillate a bit. It basically is a waveform that, by trial and error, I optimized on a different setup to semi-reliably produce glitches that disrupt the operation of this CPU. So, there's a particular set of phase offsets that seem to work and that sort of thing. And it's not super exact by any means, but I got some parameters that seemed within the range that would often work, and then I've been kind of porting that setup over to this logic controller, like an industrial device that runs on the same CPU, but I don't actually have source code or a firmware binary for. So on this device, this is like a device that would actually be interesting to get the firmware out of, and it makes for a more interesting real-world test. So, and this setup had actually been starting to give me some interesting results. This board here that might be new, since if you've seen this before, this one's probably new. I added a little RF amplifier on there to get a stronger signal out of reading back what's going on the core voltage rail to see what the CPU's up to. So I can actually get a pretty clear picture of what the CPU's doing at a kind of zoomed out scale. So, I can see, like, when is it running loops of this particular size, when does its operation change, when does the CPU start processing something, before it actually sends the results. So those kinds of things show up on the power trace. And this is the board up here that we've been using for a while to do voltage glitching, and it's basically just a fancy MOSFET H-bridge, or half-bridge rather, but designed to pull up and down really fast. And so actually I got a neat eval board for an even faster driver that I might swap this out with at some point, but right now the driver board doesn't seem to be the limiting factor in my experiments. So the pieces that I have so far, to enumerate them, I have this amplifier that lets me have a very sensitive ear to the processor's activity, so I can hear what it's doing even if it isn't communicating that externally. And then I have this setup over here that's just a more convenient breakout for the IOs, so I can communicate with this thing without the other board stacked on top like usual. Hey Tuco, who brought me a bolt this time? And then a bunch of this other stuff is just breaking out IOs. This resistor and awful soldering mess around the CPU is me breaking out the CPU's 3.3 volt rail and adding an RC filter to quiet it down a bit. Wow, I'm getting some weird encoding glitches on my laptop here that's watching the stream. I wonder if any of you are getting that. I can't tell whether it's on the read end or the write end. But yeah, anyway, this cat really seems in the mood to play. Also, it got really windy outside all of a sudden. So, glitch board that lets us introduce faults, filter that quiets down the CPU power supply so that the traces we get out of here are cleaner, a bunch of convenience over here so that we can attach to various signals. I did already break out the signals for the SPI flash. There's also, so there's 3 serial peripherals on here. The actual firmware is stored internally on the processor, and that's what we're interested in. But externally, there's an SPI flash that includes the PLC logic program, so it's like the high-level language program that this processor runs in its kind of runtime environment. And then there's an MRAM, which is a non-volatile memory that it uses for program intermediate state, for settings, like basically the program's variables. Then this big boxy thing up here is the real-time clock that communicates over I2C. And it's backed up by a supercapacitor on the bottom board. But I have the real-time clock disabled, and the firmware just always reads back the date as all zeros, but otherwise it keeps going fine, so I just have it disabled to simplify the system. So I might still, I might still be interested in having that on traces just to see when the CPU pulls the real-time clock, but from my investigations on that so far, it looks like the CPU doesn't communicate with the real-time clock very often, just in the really obvious times you'd expect, like right after boot and when it's refreshing a clock that's displayed on screen, or when it's, when you set the clock in the menu. So I don't think that's really worth going into much. But I still think there's some interesting investigation yet to be done on the external flash and MRAM. I took a quick look at it when I was first investigating this just to see if it looked like there was any way, any easy way to gain control flow, but as far as I could tell, it looked like the SPI flash was just a copy of the PLC program in pretty much the same format that you would find on the SD card, and it didn't seem like there was necessarily going to be any like easy ways in. It looked like a pretty straightforward binary file. Not the kind of thing that would have a bunch of dynamically sized data structures and parsers and stuff. And then, let's see what else. The MRAM didn't have much in it, and it wasn't really reading it much, so I figured that was probably not being used by the operating system itself, or the runtime itself. That was more for storage for the program itself to use. But I didn't really look too closely at it. So, anyway, glitching was going along just fine, and I'll get a little more into that one with some visual aids, because I have some video time lapse to talk over with regards to that. But basically, I was having a fine, jolly old time glitching, and then I bricked the darn thing. So now I've got a little diversion to try to unbrick it, and also maybe to understand how I bricked it, so that I can potentially use that as a way of understanding the device, or potentially getting more information out of it. Okay, seems like there were encoding issues. Yeah, sorry about that. I don't know what's going on there. The machine that usually handles that seems to be running fine, but I don't see any issues going on right now. Oh geez, now I gotta pop out the chat. Somehow I managed to make it super tiny. I hear you, little cat. Okay. Well, cool. Let's see if that continues to be fine with the encoding. Oh man, Chico sure is yelping. Okay, so yeah, I was in the middle of a glitching experiment. Well, actually, not even in the middle. I had just started this glitching experiment that I was hoping would run all night, and then I noticed that there was a streak of red failures on the screen, and I go reset it, and it doesn't seem to do any good, and then, hey, Tuco. You just kicked that way over there. I'm not gonna get that. So yeah, I noticed the string of red failures, and then now every time I boot it up, it fails too. Well, so it's running right now, but you couldn't actually tell. And so if I have a reset button right here. So if I hit reset, you can see the LCD turns off and then back on. So it's not, you can already see some signs of life. And then if I go to the O-scope, so I have the O-scope triggering on this reset pulse, which is down there on D7. And then you can ignore that activity on D0. That's just my debug probe. I have its waveforms on here just so I can make sure that nothing I find interesting is correlated with my debugging, which was the case a little while ago. So yeah, if I hit this, you can tell that the processor is going through some kind of boot sequence, which means that either this is the onboard ROM, because this processor does have a ROM. I think it's likely the ROM is disabled, but I don't really know for sure. So one experiment I'd like to do that I haven't been able to do yet is to collect a power trace of this processor, on some other dev board that I have control over, programmed to enable or disable the boot ROM, and then get power traces for each and see what that generally looks like. But so far, it's been my assumption that the bootloader is probably disabled, but I haven't really looked into it yet. Oh, here we go. Got a mouse back. So yeah, so here's the reset pulse coming in. Here you can see the power waveform during the actual reset, and it's interesting that it changes. I'm not really sure why. Then we come out of reset. There's a couple different phases here. And then this might indicate some communications. So, I'm hoping that what's going on is I corrupted something in the external MRAM. I might have, during one of the glitches, it might have caused, some subroutine to run that would have written some bad values to the MRAM, or something else could have happened. A number of things could have happened to corrupt it if that write enable pin had already been asserted. So I'm hoping that what we'll find is if we hook up the logic analyzer to those SPI buses, that we see it read a bunch of stuff, and that maybe the thing that it reads right before crashing is relevant. And I'm also hoping that we can get some traces of what it's doing, and then analyze those, some now and maybe some later, but then also try to wipe the memory contents and see if I can get it to boot again, because it would be nice to know if this thing is bricked for good. Yeah, that's about all we got right now. All right, so I was thinking I would do this using the Salier logic, since that would, in my experience, it's really nice for collecting giant traces of SPI stuff and sifting through it later. Whereas I think I could do that with the scope, but I don't know if that would be compatible with the time window that I want that capturing for the other signals. So I think it might be handy to have a second analyzer just for these buses. So what happens, I have this logic here. Tuco, what do you want, little cat? Let's put on a grounding strap. You just want bolts. Oh, I had a diagram of where all these things go. It is on the other computer. Where is my remote? Okay. Of course it opens on the other monitor. Why would it open on the same monitor I clicked on it on? That would be bizarre. So yeah, basically I traced out the, let's get that overlay off. No, this one. So yeah, the old overlay the front and back photos and line them up and trace the traces you're interested in and label them trick. So this was useful for wiring everything up in order to break out the signals to analyze them. You can tell a few things off the bat here. Off the bat. What a weird sports analogy. So a few things jump out here right away. The two memory chips share a single SPI bus. They just have separate chip select and write protect pins. So we can get away with just probing a couple, well, all the signals that we care about on this chip. So it's chip select, data in, data out, clock, and write protect. Then for the MRAM, it's in a less convenient package, but all we really need is write protect and chip select from here. So you can grab those from a number of places. I think I grabbed write protect off of this giant pad here and chip select off of this resistor bank. So the other thing I wanted to point out is these two giant pads, because this might be a clue as to unbricking this thing. So that's attached to write protect on the MRAM, which is the faster non-volatile storage for settings, and the ground plane. I was thinking that this other one might be for, like the other write protect pin or something symmetric like that, but actually this was ground, and the best thing I can figure here is that this is either a location for a jumper that isn't attached, or it's actually intended to be something where you just push tweezers or something across this to short between write protect and ground as a factory reset. Because I'm thinking the way that might work is early in execution they might sample this pin to see if it's being pulled down, to ground externally, and then enable some kind of reset procedure. So after I capture a trace to see what's going on, that's going to be one of the first things I try, since it seems like maybe that's an intended way of recovering it from a state like this. But if this turns out to be an interesting sort of crash, then maybe I want to experiment with, crafting my own MRAM payloads to see how this responds, or potentially even having an MRAM emulator that I attach in the FPGA. Oh, Tuco's right here under the table. He's hanging out in foot space. Does Tuco wanna hang out with my foot? I think he wants his own space. Okay, I think we need the other computer. Let's get the logic hooked up. I think the wind is setting off car alarms around here. It's weird. Oh man, have I used up all the good grounds? I couldn't have. There's so many good grounds to choose from. I mean, there always needs to be more grounds, really. I think I'll put this over here. Oh! This is set up to monitor the clock going into here because... So the thing that I had just changed about my glitching setup that I was super happy with was I added a variable clock rate so that it speeds up the clock when the device is booting, and then when it gets close to when I want to run the experiment, it slows it way down. And so I was monitoring the clock on the O-scope to see if that was actually working correctly. I hope that's not what bricked it. Tuco, you're standing on the keyboard, honey. Tuco. He's also blocking my view of the schematic I was going to reference. Oh, cat. At least he's cute. He's a cute little obstruction. Okay, fine. I guess this is a good time to go to the videos. Since I can do that without the computer he's sitting on. All right. So, where did I want to start this adventure? Let's... Oh, I think I might need to go full screen for this. Oh man, I can't take Tuco off the screen. Let's just make the video smaller. I think I can take the scope off. And then you can see the scope in the video, which is much more important than the scope right now. That's better. Okay, so this is an earlier experiment. So this is the first kind of glitching experiment that I tried here that actually worked at all. And this is basically, you know, I'd isolated the region of interest down to between these two packets. So this packet is, this is an HTTP request. In this case, it's a post, but it would usually be a GET. I'm using a post because I can cause GPIO side effects with that. So this is the HTTP request coming in. There's the first packet of the HTTP response. In this case, it's the headers, but none of the body yet. So I don't necessarily see the data for index.html for some time later. It's actually on kind of a deferred event handler of some sort in this PLC's main loop. But in this packet, you at least know that, you know, you have an HTTP content, you have an HTTP response type, so you know that it wasn't a 404, you know that the path was valid. It also has, I don't know if they bother including a content length. Yeah, they do, they must. Yeah, so that includes the content length, the MIME type. So you know that it's done the file system lookup that we're trying to glitch between these two packets. So beyond that, you really want to have a stable time reference that correlates with the code that's executing here, so that you can kind of step through it and find the interesting regions to deliver the glitch, and then have a repeatable way of glitching that particular region. And so here, that's not what I had. I had this other thing, which was, I can demonstrate what's going on here, because it's a really short little Python script. Maybe that's on the Raspberry Pi. Let's get that window on the screen. I'm logged into the Raspberry. Yeah, so this is basically the program that's responsible for that trace. So part of this is just, it needs to log in to the management interface, and of course they use something that's basically, you know, kind of a not especially great, but not especially, like, it doesn't seem to be that much worse than like HTTP basic auth. As you can see, it's based on CRC32 as a hash function. But yeah, so that's just used for like a short-lived authentication token. And then the actual command is an HTTP post. And then I do this message click thing, which it's normally used for a GUI that emulates the front panel arrow buttons. So the idea is you can write a logic program for your industrial controller that has some ability to display messages to a UI and take arrow key input. You know, it has like arrow keys and an OK and an escape button. And so what I did is I just put a program in the PLC that wires up one of those inputs to one of the outputs I have, and now I can make this request to deliver one of those, you know, GUI button clicks, and then it gives me a GPIO. So that GPIO is, that is what we were seeing in the video that I just closed. Let's open that again. So this signal up over here, which is where the scope is triggering, that's the GPIO that I'm toggling as a side effect of this HTTP post. So with this post, it's sort of a weird request because normally that would just be used to submit like an AJAX request to ask the little tiny web server on here to issue that button toggle. So in addition to that, I'm getting a copy of index.html back, and this seems to be not quite a bug, but maybe an unintentional feature in the way they've implemented the web server. So you can do that post on not necessarily any URL, but at least index.html works, and I think it might be content type based, so it might be something that works on anything that would have given you an HTML page. So that might also be some clues into how their web server's been hacked up, because it does seem like this was based on a fairly typical LWIP HTTPD example, but then a lot of things were added to it by them and by some middleware company. So then my hopes for this were kind of dashed because it turned out that this GPIO happens like right at the end of all the processing. So like it's basically finished with everything related to the request by the time it triggers this GPIO. So it's useless for triggering any interesting glitches. And it took me a little while to discover that because even though it looks kind of obvious in this waveform display, I didn't get this clean of a display until I built that new amplifier add-on. So thanks to the amplifier, it's really clear to see, this is the main loop, and this is this special processing that it's doing, and you can even kind of see that there are multiple phases it's going through. And these long sections are probably loops where it's processing a string or searching a data structure, and then these sections in between are probably control code, and these are probably shorter loops. So you can start to get a sense for how the processing is actually structured here. But in this experiment, I have the chip whisperer and in turn the glitches triggering off of this signal. And this is just being generated by the Raspberry Pi. So in this setup, the actual interface between this PLC and the outside world is over Ethernet. But because I'm doing all this wacky stuff with the clock, I need kind of a weird Ethernet device that I can underclock, and that when I underclock it, it behaves exactly the same as this device in exactly the same weird non-spec compliant ways that it will. So for that, a while ago, I ended up making a little thing that I call GDB Ethernet. It lets you basically run a GDB script that creates a network tunnel using a microcontroller's Ethernet peripheral. So I have that running on a Raspberry Pi. And the top two traces on the analyzer, those are just showing the debug traffic between the Raspberry Pi and the other microcontroller that's acting as my Ethernet peer. And so you can see there it's spending a while oh, right, this mouse, because it's a recording. So right here you can see this is it transmitting a packet into the Ethernet buffer on the microcontroller, and then it's like issuing the write, or it's getting ready to issue the write. But then this, can I zoom this easily? Not that way. Oh, I don't know if I have the screen zoom set up on this computer. That would be super useful. It doesn't seem to have the thing that it says it has. Oh, okay. I guess that is set up. I just forgot which modifier key, apparently. So, if we embiggen the scope down here. So, yeah. So this is the trigger we've got. And, well, this is the GPIO we have, which is not useful as a trigger because it occurs after the region we're interested in. Ideally, we want something that's synchronized with this signal, this kind of main loop iteration here, and we really want to trigger like right there, and then add an offset to that, and then glitch. For this round of experiments, I was using this signal here, D10, which I was generating on the Raspberry Pi. So you can see here, here's the Raspberry Pi copying an Ethernet packet to the Ethernet buffer, and then the Raspberry Pi toggles that GPIO high. And then the Raspberry Pi sends the Ethernet packet, and then immediately afterwards you can see the Ethernet packet actually going out here on D14. So already we've got a bunch of variable latency here because there's like Python code running on a Linux machine between this GPIO and this Ethernet packet. But even if we had something that was perfectly synchronized to this Ethernet packet, that's not actually what we want, because it turns out that there's a little bit of a variable latency between the Ethernet MAC actually processing this packet and the interrupt happening on the processor. So really, really what we want is not even the interrupt. We want when the main loop gets around to processing the HTTPD traffic that's been queued up in some work queue somewhere. So that's why there's kind of a complex series of events here. We really want to wait for the, we want to wait for the experiment to begin. We want to make sure the Ethernet packet happens, and then we want to synchronize with the main loop. So none of that's happening right here. And in this experiment, I'm just having the chip whisperer trigger directly on the Raspberry Pi's signal and just kind of casting a wide kind of shotgun spray of glitches everywhere, and just to see if there's anything that sticks out in this area, before I had a better way of doing it. So let's get to the good part, because that's way too slow. So you can see the pace of things here. It's pretty slim pickings here, and the glitch is really jumping around a lot. So you can see that we're kind of holding things still relative to the GPIO still, because even though the GPIO is, it comes too late to actually be useful for triggering the experiment, I was still triggering the scope, using it as a way of measuring how bad everything else was. And yeah, this shows it's jittering by like a millisecond, which is crazy for what we're doing. I'm searching in the neighborhood of 5 to 10 clock cycles at a time, and that would be what, like 20,000 clock cycles or something. So what's going on here? Did this stop recording? Did my video grabber die? Okay, I think that was one of the less interesting experiments. One of these, I still got some greens though, which I wanted to briefly point out. See, these were really unreliable. And then I reset it. Let's go through this faster. There were some greens there. So you can see about how frequent they are. Let's see if we can get that again, or did I go past it already? This is a little easier in the video editor. I feel like I saw that on the smaller monitor, but not on the bigger monitor. And then anyway, I think you might have seen those, or maybe you didn't. You can probably get that they're elusive. Anyway, I found a couple of these glitches, like over the course of running this for a few days. I found like maybe a dozen of them, where with this kind of shotgun approach, I was hitting something that apparently was causing it to break out of a routine, which was doing like a template substitution on that index.html. So that was interesting. I ended up getting a version of the web page with the variables not being replaced in some areas. Anyway, I think we have better traces later, because this gets much better. Oh, is this the one that actually starts working? Oh yeah, there was a green. So these are not frequent, but I think this is the one that has a couple of these. Man, I have seen the thread on why VLC doesn't have a single frame backwards button, but I think it would be useful, even if it needed a cache. Okay, there's one. So, I don't know, with the time lapse here, you can't really quite see what's going on, but it was just a slightly different length, different hash, and then, we can go look at the trace. There's a PCAP file for this, but yeah, it was basically just some variables not being substituted. Not really the kind of glitch I want, but an interesting clue. Also in here, you can kind of see what region we're glitching. It's kind of in between these two kind of loop-like or kind of string processing-like regions. There's this, so my guess is that this is something that has to do with the HTTP or the TCP/IP stack processing the packet, and then this is something to do with the web, the index.html templating engine thing. So this might be getting close to where the file system lookup happens, but it's jittering so much that it's really hard to tell, and then often just breaks for stupid reasons like that. Some more greens. So yeah, so then I thought, well, since, I don't know, in kind of parallel to this, I'd been trying to develop a theory about how the timing on this device works in general, since it seems like, there's this main loop that processes the PLC program in iterations. It's also, I just saw a comment in chat. Is that an important laptop that's Tuco's sitting on, or did Micah get a decoy laptop? That is an important laptop. I changed tactics. I was going to do something that required it, but I'm doing something else instead. So here he is bossing me around again, basically. The laptop that would be changing the stream title is actually up on a stand where I can read it now, which is why I don't just ignore the chat all the time. It is a little chilly in here. I don't have the heater on because it's been relatively warm lately, but maybe I need to turn it on this evening. Okay, so yeah, I'd been trying to develop kind of a theory about how the PLC's, how its processing worked. I had previously been seeing some weird artifacts, like if I had underclocked the PLC to a certain degree. So I thought I was seeing something where when I underclocked the PLC enough, it stopped responding to HTTP requests. It would get just the header, but not the body. That turned out to be a crazy debugging goose chase where there were bugs happening, but I was also just perceiving the problem incorrectly. So yeah, that was actually an issue where there was kind of a latent bug in my GDB Ethernet bridge where it would end up dropping. It was like, one of these classic polling problems where, it was just, it wouldn't check the receive queue unless there was also something pending in the transmit queue, like one of those kinds of bugs. And the only reason I hadn't caught it was that when you're doing a ping, you're always getting enough packets both ways that the queues don't clog up. And when I was doing TCP, then you would just get TCP retransmits covering it up. So, yeah, it turned out that I fixed that bug, and then that made a lot of things easier. And I think that, plus maybe fixing some timeouts elsewhere that were set too low, got HTTP working down to the lowest clock frequency that I'd gotten it working on the dev board, which was like 6.25 or something megahertz, or no, 5.6 megahertz. Whatever I'm operating it at now is that frequency. So that was good news. That was really nice, actually, because I thought that I was stuck not underclocking it much. But anyway, that led me to kind of this fake theory that the main loop was timed based on like an RC oscillator because it wasn't changing as I was changing the crystal frequency. That turned out to be total BS because it turns out that was when I was measuring the the vCore activity without the amplifier, and I was actually getting more noise from my debug rig than I was getting actual CPU activity. So I think what I was seeing when I was averaging over a bunch of runs in the scope was the single wire debug traffic between the Raspberry Pi and the Ethernet device. So that was embarrassing, but that also explains why I was having this period that kind of ran at, it was like 100 milliseconds, and then it turned out that the reason that was so slow, so yeah, that was also part of it. It wasn't just that there was a queuing problem, but I was getting these 100 millisecond pauses in my GDB Ethernet driver, and that was just related to, I was having GDB continue and then stop in order to run some native code to talk to the Ethernet PHY, because I didn't want to have to talk to the PHY in Python code. Talking to the Mac was enough. And it turned out that that was fine, but it was really slow. It takes like 100 milliseconds to do that. So instead of speeding that up, I just have it only do that when it needs to detect a link state change. So it's hacky, but it works well enough. And so now my GDB Ethernet is running consistently not terribly slow. And you can see that I'm still monitoring it up here just to make sure that it's performing, but it's been doing all right. So then I'm just monitoring one of the Ethernet twisted pairs for transmit and receive so that I can actually see the packets go in and out. Yeah, here you can see quite a few of those glitches where it causes the substitution to fail. So you can kind of get a sense for what the region is, but very noisy. So let's see, where's the next one where I actually fix this? No, that's more greens, but still. I think it was this day, 21st. Oh yeah, this thing. This starts out with, I think let's view it full screen. All right. Now I have like a little control that I can use to time travel. So, oh, I can watch past me check her phone. Oh, is this? I wanted the one where I'm looking at the PLC program. Yeah. This is what I did. So, previously I had been, previously what I had done, so this is the kind of visual programming language that the programmable logic controller uses, and it kind of mirrors kind of old school relay wiring diagrams. So here's the cursor key that I have connected directly to output Q1. So this is what was generating that trigger we were using on the oscilloscope earlier that happens too late to be useful, but at least is synchronized really nicely with the events we do want. Then this is my latest edition. So I was reading through the manual here trying to find logic elements that would allow me to create a change on the time scale of just a single main loop iteration. And I found out that these output elements also act like logic flip-flops. So they have an output that returns their state as of the previous cycle. So this is an inverter. So you can see it's just an oscillator here. So on every clock cycle, I'm just taking the previous state and inverting it to give me the next state. And so this just gives me a toggle that goes up and down every single time the main loop evaluates the PLC program, which is really nice because now I have a clock. And I can also see when the main loop is busy. So, man, this is even time-lapse. This is really slow to actually download. I mean, I'm probably dropping a bunch of its packets for all I know. This is going over an Ethernet bridge to the GDB Ethernet thing. Okay, and then I was testing this using persistence mode on the scope. So here the scope is still triggering on that same GPIO signal from before. This is the old Raspberry Pi signal that we were triggering the previous glitch experiment on, but it's going to be jittery. Then here are all the edges that we're generating on that new output that just toggles every time the program's evaluated. So you can see one of those is going to be lined up with the, the I/O that we've had the trigger on. You can also see it pretty well follows this pattern that we're seeing in the power waveform. So it does look like this is running every cycle. you can also see it gets blocked whenever the main loop is busy. So we also have a nice indication of, if we ever need an indication that the main loop is busy and we don't need it on a latency of less than this iteration cycle, then we can just look for longer than usual gaps between these pulse edges, and now we have a trigger signal for when the main loop is occupied. So here I was collecting some long persistence traces just to see how stable this is. So you can get an idea that at least within this contrived experiment, you can see the main loop here, and at least within, a couple hundred microseconds, it's staying pretty stable, but that the errors do compound. So you can see that this is much less jittery than this. So there isn't any kind of external time reference. It's just based on how long the code takes to execute, probably. You can also see that even though this is lined up pretty well with... So the scope is synchronized to this edge right here, but it's also pretty well lined up with Ethernet packet. If you look closely, you can see a couple of pixels of difference between the actual trace and the persistent ghost image, and it does jitter a little bit. And if you zoom in, you'll see it jittering by maybe, a few bit periods on the Ethernet. So it isn't a lot, but it's enough that that would be not the best reference to use, even if the piece of code even if the thing I wanted to glitch was right here, which it won't be because I know that the code I want to glitch happens before this packet even goes out. But this is not totally synchronized with the code that's executing in the main loop. It's close, but only as close as the Ethernet MAC and the CPU ever are, which is not that close. Then you can see over here, this is not just the usual jitter between the MAC and the CPU. It's also got the jitter, basically this amount of jitter, which is approximately all the different amounts of time that this could take to run, presumably. And, there are likely cases where, some of these I think are abnormal cases where something weird happens while I'm capturing, and I think some of these are just like an interrupt happens in the background or something else interrupts this loop. Oh, I was trying to get this to do a histogram, but I think that's only going to work on analog channels, so I gave up on that for the moment. Anyway, let's go through a faster version. Oh, here we go. Yeah. So then I go back to the FPGA, and I was going to write myself a little triggering engine that looks for, it just looks for the sequence of events I want. So here, that's the trigger from the Raspberry Pi, and then I'm looking for a certain number of Ethernet edges, so I want to kind of get into the middle of the packet, and then I'm looking for the next edge, or I forget what the heuristic I used. I think it was the next edge on that clock. But so I'm basically estimating where I think the last edge here before the gap is going to be without actually having to wait for the gap. That's the particular game I was playing this time. I don't know if I need to wait for that. I don't know if I need to trigger in less than the time one of these periods would usually take. If the answer is no, then I can just wait for a longer than usual gap. Like I can basically just set a watchdog timer that's kind of the maximum length I would usually expect one of these periods to ever be. And if that watchdog timer expires, then that's when I trigger the chip whisper. And then at some measured offset from there is my glitch. But if I do need it to happen before that time, then this heuristic is kind of the sort of thing I'll need to do. But so now you can see it's not perfect. Sometimes I end up missing it, and so like this is it operating correctly. You can see a couple of traces where it ends up going like one iteration too early, which isn't bad. It isn't that bad. It'll just make my glitches less effective. I think I decided that this was good enough, and I started a glitch experiment using this. Oh yeah, these are really slow. Let's make this... Oh man, that's That codec issue was on my end. That was not the stream. Let's try this one. Okay. So this is getting closer to what I actually want. So here, is this what I'm triggering on? D10? I think that's it. So this looks like it's working. So D2 here is the signal from the Raspberry Pi. Oops, let's zoom in there. So yeah, on the top here, D0 is just one of the debug traces. So this is the bus where the Raspberry Pi and the Ethernet peer microcontroller are communicating with each other. And this is the Ethernet from the Raspberry Pi peer device to the PLC. And this is the response from the PLC back to the Raspberry Pi. This is the trigger signal from the Raspberry Pi saying, I'm about to send the packet you're interested in, which is literally just like a hook in the GDB Ethernet driver that does like a string compare on the packet contents. And when there's a packet that has the string I'm interested in, it sets the GPIO high. And then there's another string that resets the experiment and sets it low, so they don't have repeat triggering. So then this right here, D9, what is that? That's the GPIO signal, so that's the one that's synchronized but too late. So this is the window we're interested in, and you can see the corresponding gap in the toggling on D3. So this edge right here on D3 is the one that we want to use to trigger the experiment, and it looks like D10 is successfully finding that edge. So that is the experiment we're running. We're triggering there, and there aren't any glitches yet, but there you can see I just added the glitches, and then it stopped. And then I unbroke it and started it again, but it's really slow. I think I went back into the Verilog to try to. Oh yeah, I think the next one is going to be with the variable speed clock. So then my next priority was making it go less slow, because it's so slow. I mean, part of it is that after I reset it, which I want to do before every experiment, because most of these glitches are going to leave the processor in a pretty weird state. I want to reset it before every experiment. I've tried doing glitch experiments where I don't do that, and it's pretty perilous. I've considered doing some kind of hybrid strategy where I try doing it without a reset, and if it responds weirdly, then I reset it. But so far, I haven't gotten around to implementing that. So far, my approach has been to try to just make the process of recycling it and getting a fresh boot of the processor as fast as possible. So the next thing I did toward that goal was to give it a variable speed clock. Since I want to underclock this as much as I can while I'm doing the experiment, just to make the glitching easier, because then my glitch edge rate will be higher relative to the CPU's operating rate, and I can get away with less exact timing all over the place, and I can kind of get more out of the timing resolution that I do have with a slower processor. So that's all desirable, but it sucks to make the processor take like 4 times as long to boot. So I also don't want to change the clock rate very abruptly if I can get away with it, because this device has a PLL where it multiplies the clock that I give it by a factor of around 5, I think. Yeah, about 5. And then that's the rate that it runs on internally. So there's this control loop at play that it's measuring the error continually between these two clocks, and it's assuming that the error is relatively low. If I give it a clock that just has an error much larger than what the PLL can deal with, then I would expect the resulting clock to be kind of glitchy, which isn't something I want when I'm just trying to get this thing to boot and not trying to glitch it yet. So that's why I did my best to smoothly adjust the clock, but since I'm just using an integer divider, there's still just a bunch of steps. I just tried to pace the steps out relatively slowly. So I think that's what this starts doing soon. Oh. Was that the one where I bricked it, actually? Hey, Tuco, relax, little guy. Oh, yeah, okay. this this was just so fast, I missed it as it went by. So the yellow trace here is the clock, actually, and even though it's really way too zoomed out for you to see the actual clock edges, you can at least see that the clock changes, and it changes somewhat gradually. So basically this was just booting it up, then ramping. Actually, I think this is the reset right here where it's triggering. So I think this is when it goes into reset, it ramps the clock up, and then the processor comes out of reset with the fast clock. Then after 60 million clock cycles, the FPGA starts ramping the clock back down. So that worked for a while. I'm starting to run that, and I'm hopeful that this experiment is going to work out pretty well. You can see this is guessing, well, so this D10 is the kind of synthesized trigger edge that the FPGA is generating based on the trigger from the Raspberry Pi up here and the toggle signal that's coming out of the extra GPIO on the PLC. And then, so D10 is the FPGA generating a trigger that goes off to the scope in the chip whisperer. Then D11 is the corresponding glitch pulse, which is 190 clock cycles after that and sweeping through that range slowly. And then you can see this green spike is the actual voltage glitch showing up on the analog channel. And then the processor is unhappy with that in this particular experiment. So yeah, sometimes it's unhappy, sometimes it's not. I wasn't really expecting it to get interesting until this went a little later, but my plan was to just sweep through this range anyway since it was late and it seemed like a thing I could just run overnight. Especially since this made my experiments almost twice as fast, since I didn't have to wait nearly as long for the boot. So this seemed fine. Jumping ahead here. Oh, there's the failures. I'm trying to find the moment where it failed, but I already looked at it and I don't think it was that interesting, but okay, so here it is running pretty normally. And there it goes. And it just stops responding. And this particular scope trace is not unusual. Like, it would often, a particular experiment would often end like this, but then you just reset it and it would move on. So, yeah. And then, as we saw on the scope, we can reset it now, and it shows some activity on the power trace, but it doesn't really do much. Sometimes I get garbage pixels on the screen, which is weird. I'm not really sure why that's happening. That's actually kind of encouraging, because maybe, if it is reading something from MRAM, which is causing it to crash, then maybe I can exploit that for, for my own amusement. So there's more scope traces. Okay, so I think that's enough of that, and Tuco is no longer sitting on my laptop, so let's get the schematics back up and try to attach the probes. Where is Tuco? Oh, he's over here. Great, gotta have Tuco for all the Tuco fans. Oh man, I'm on my way to having a hovering Tuco camera so that Tuco's easier to keep in frame at all times. I'm not quite sure whether it should be like automatically piloted or whether it should be fan controlled or whether I should control it or some combination of these things. But my plan is basically to have a camera on a gimbal on wires and then the wires on winches. That's pretty much it. And closed loop feedback, of course. Wake up, Lappy. laptop. Did you forget how to laptop? Oh my god, what happened to my laptop? Tuco, did you break my laptop? Tuco, what are you doing over there? Alright, we're back. The laptop is, I think Tuco kernel panicked the laptop. Tuco, how did you even do that? Well, first the computer was all, you shut down because of a problem, and then it went all black screen. Computer. Oh, no, come back. This might also be having a problem related to not knowing where the monitor is. Now there's just a cursor on the screen and nothing else. I think I'm gonna reboot it. That's okay. I didn't need those schematics anyway. We can just plug things in and figure it all out. It'll be fine. It won't be that hard to figure out anyway. Bong. Alright, let's let that boot while we put wires into things. Oh, actually, I need to plug in my Cellier. Ooh, maybe I will turn on the foot warmer. There was a bolt on it, of course. Okay, we were still trying to find good grounds. Alright, I think that should be fine. And yeah, got this monstrosity of glue down here, which everyone must behold. Oh, Tuco is all up in the wanting things today. It's not time to be Servo AF. So yeah, this is me when I don't have an SO8 test clip. I think Tuco wants to go outside. I don't have quite as much exposed header as I would like. Hope these all make good contact. Ah, this camera is so in the way. Where am I even attaching these? Okay, I need to move this camera so I can actually see what I'm doing. The downside of using 40 gauge wire is it's really hard to see where the wires are. I'm looking for this signal, which goes via invisible copper to this pin. And I think its neighbor over here is the other signal I want, which goes also via invisible copper over here to that resistor bank. other two neighbors there are I2C for the real-time clock, which I guess I'll throw one of those on there since I've got a spare pin on this header. Yeah, Tuco's being whiny right now. Oh, cat. Let's have the camera on the screen. Man, that wind sure is blustery out there. Alright. Let's get logical. I have this handy remote reset button in this virtual machine over here. I can push that and reset the PLC without having to reach into this mess of wires. All right. Let's have all of these. Oh, that's interesting. Please have 3.3 volts for me. Thank you. Cool. Okay. Let's just see what these are like for a bit. Huh. That's not good. Oh, maybe it's time to just probe around and see what's alive with the O-scope. Because, geez, that would be not so good if we're not getting any activity on these memory buses. We wanted this. Alright, let's have... Alright. Start poking around. Just going for this resistor bank where all the SPI signals are located. You know, if this isn't an external memory related thing, it's gotta be... well, I don't know, there's still a couple of possibilities. It could be bootloader, it could be internal flash, it could be internal EEPROM. Oh, can I have DC coupling, please? Let's also get a little closer here. Can I have that schematic now? Yes, computer? Did it just turn off because I didn't log in? Tuco. You're not even in your camera. Oh, that's I squared C. We're getting a little blip there, but that's when reset is asserted, so that's probably not intentional. Oh, now the computer's booted. It's also I squared C. Oh, why do I not have the scope on the screen? Sorry. So the I squared C trace that I was getting was, oops, not that. Yeah, a little glitch at the beginning of the reset pulse, which is probably not relevant, but kind of interesting. GPIOs, maybe? No? This is not so good. I wonder if it's worth checking the JTAG interface on this, which wasn't open before, but who knows what state the processor's in now. I wasn't intending to do that kind of glitching on this, but yeah, you take what you can get. Alright, schematic? Can I have schematic? Yes, I can have schematic. Okay. Yeah. So I should definitely be seeing something on these two vias if there's anything alive on the SPI bus. Oh, so the LCD is doing something. I can't tell whether that's because of something the processor is doing, just because of some GPIOs changing like output state or something, or whether, you know, this might just be some other functionality triggered by the reset on the board level. But I'm just gonna try poking around the LCD connector and see if I see any signals going to the LCD. I haven't actually figured out which one of these are normally data, but I'll just try a few. Oh. Oh, okay. That looks like a packet of some sort. Let's zoom into that. Well, if this was running the ROM bootloader, and only the ROM bootloader, we would certainly not be seeing it talk to the LCD. Well, this explains why I was sometimes seeing this LCD screen fill up with garbage if it is actually sending to the screen. Well, this is a more mysterious brick state than I expected. Should probably see if I can get them to send me another board. Actually, it occurs to me I'm not sure whether this is a parallel or a serial LCD. It might be parallel. There's really enough wires for it. Let's zoom back out. Oh, that is way too zoomed out. So you can also start to see a little bit of the power trace going on, like, I don't have like reference power traces to compare this to, unfortunately, because I hadn't really looked closely at the boot cycle until now. Is this just where it gets hung? Well, there's something distinct there. Oh, Tuco, you're standing on the laptop again. Are you gonna kernel panic it again? How did you even do that? So where in relation to all that was the LCD activity happening? I think that was a clock we had found. Yeah, kind of right around that little blip that kind of shows up in the power trace even when I'm not probing that line, which would make sense. It's drawing to the screen right there. So that's interesting. Pretty early in boot, but certainly not... What state is that write protect pin in? This is that MRAM write protect. So, I don't know. It's still tempting to try pulling that low, since that was an experiment I wanted to try, but a hard time imagining, well, I mean, it seems like the problem has nothing to do with the SPI peripherals. But there's still my curiosity that perhaps that was used as, like it doubled as some kind of configuration jumper. So I'm gonna try that just cause. I'm going to use the multimeter in current mode to pull it down. Now I'm fighting against the microcontroller there. It's 17 milliamps if I touch that to the write protect pin. Let me try doing that and then immediately resetting. That gives me 0. Like it stopped pulling. Try resetting again. Still gives me a similar power trace. Let's see if that's reproducible, because that's interesting. Let me get the meter in this frame here. It does seem like this means I somehow wrote to the on-chip memory, which is just baffling to me. Like, why would that even be enabled for writing at this point? So, okay. Ground, and so I'm going to reset it. There's the normal power trace we've been, well, not normal, but the particular bricked power trace we've been observing. And if I momentarily touch this to write protect, you can see that the meter jumped up to 17 milliamps, so I'm fighting against the microcontroller pin. But if I hold this and reset, well, it's actually inconvenient to do that because that doesn't trigger the scope, and this is just a momentary. So I'm just going to attach this and then right away click the toggle, and I think we'll see it stay at a low current consumption. So let's just poke through that Kapton. Okay, so I'm fighting it, and now it stops fighting. It's not like a 0, but let's see if the SPI shows any activity while I'm shorting this. I mean, I guess I have that on the Salier logic too, but let's get this on the scope. Not seeing anything. Okay. Man, it would have been really convenient if this was something in the SPI memory that would have explained the symptoms so far, but now I'm starting to run out of ideas. Let's just make sure we're not seeing anything on here. Oh, I didn't actually mean to run the experiment. I just wanted to reboot it. So now I'm waiting on the experiment to fail. Okay. So I can trigger this a few times. We see the scope update. I'm going over here to the logic, and we've just got some of these big state changes when I reset, but no actual data. So, it is looking like this microcontroller may be bricked in a way that I don't know how to recover it. Let's see if we see any more signals that are interesting, like any more clues. Which button do you want? This one? So I'm also going to poke around this external serial port. These pins sticking out are for the expansion bus. So that should be ground. Oh. Something changing state. I forget whether, like, which pin that is. I've got a pin out of this that I made up somewhere. It's got like clock and data out and then async serial in. That seems uninteresting. It's on the LCD. That LCD update is one of the last things I see it doing, but there's like a whole little cluster of activity around there. Oh, that's a really good sync for something. Huh. What would it be doing this early that involves starting up the LCD and then failing to write anything to it without having any conversations with external memories? That's the clock on the LCD. Could just be by some fluke the SPI controller is powering up and spewing some data at the LCD, but this seems maybe a bit more intentional than that. I just don't have this LCD broken out in a super usable way right now. There's 30 pins on this connector. I'm not really being methodical about checking them all. I was hoping to at least find one of the data bits. Well, It might be that we just have some, this might be one of the data bits, and it might just be we have like an initialization packet up at the beginning with lots of stuff going on, and then a bunch of nothing for the display. I think that might be what we have. Yeah, so this is probably 1 bit from a whole bunch of initialization commands going out over a parallel bus. I suspect we'll see another slice of it if I poke around here. Yeah, that's another bit. See that jitter? That's me triggering on the reset pulse, and then there's a variable amount of time that the chip's internal oscillator takes to start up, and then transfer control to the external oscillator. And there could also be some variability in when it detects the edge of that positive going edge of the reset pulse. But if we were trying to synchronize to the actual code execution, then that packet would be useful. But as it is, that's just another thing this chip is doing that is not super helpful. Maybe let's try JTAG. I mean, the chip is probably still locked, and I don't think that's going to do anything. Since this definitely looks like it's still executing the chip's firmware, this isn't like something the bootloader would be doing. I just don't know why it would wedge right after clearing the screen. Just gonna make sure I didn't see anything on the SPI bus either. Or not SPI, I2C. I mean, I hadn't had problems with it, failing to talk to the real-time clock before. Oh, that's right. These just had a little glitch, but nothing interesting. Meh. Anything on the Ethernet? Wouldn't expect it. I mean, that would only... I would only expect something like that if the Ethernet MAC was changing states during initialization. Oh. There's also this SD card slot. I wonder if it's trying to talk to any non-existent SD cards. Put a card in here and then just see if it gives me any useful signals. Hopefully 8 gig isn't too much for it. Oh man, Tuco is without his camera again. Yay, Tuco's a star. All right. So, first let's just see if the power trace changes. Oh! Did we get some kind of SD card bootloader, maybe? I was pretty sure there was something like that, but I didn't think it would necessarily be the easiest way in. But we could certainly try to fuzz out what file names it's looking for based on the power trace. Let's see if we can get closer to this. I should probably build a proper breakout for this. but I'm just going to poke around a bit and see if I can find anything. Ooh. It's talking to the SD card. It isn't totally dead. Ah. Well, that's a relief. Suspect I might end up wanting to hook the Salia up to that. I wonder if it has a decoder for this. I think so. Anyway, we'll cross that bridge later. Okay, well, maybe the next thing to do is to assume that I somehow got this thing into a Siemens-specific bootloader mode, which is looking for a file on the SD card, and that I need to figure out what it's doing. So I think the next thing to do is to just break out the pins on this SD card daughter board so that I can actually get them on the logic analyzer. Oh, man. This is going differently than I expected. I think it's still going somewhere, but it's a little bit weird. Hey, Tuco, do you want to go back outside, little cat? I think he wants to go outside. He doesn't want to hang out with us. Tuco, hang out over here. The laptop's warm. Okay, let's see what this adapter board is like. It is, are these no, these are 2mm headers. It's just got like it was on like a slide out drawer on the original PLC plastic enclosure, but the drawer itself is a circuit board with a micro SD card slot that plugs in. Hey, Tuco. Man, I feel like what I really want here is an emulator for the SD card, where every time you read from it, it can increment the data that it's giving back so that I can kind of fuzz out the space of file names and like guess character by character if there's a file name that this thing is interested in the directory. So that seems kind of appealing. This does have test points for everything broken out. So I think maybe some time with this and the micro SD pinout and some little wires. Oh, Tuco really wants to play Bolt. Tuco, you're under there. He's like hiding from the camera. I can barely see him. A good question from US Water Rockets in chat. Why not make an SD card emulator that prints out the files it's being asked to send? That's basically what I want to do, except that it doesn't quite work like that. It doesn't ask for files, it's going to ask for disk blocks. And so at one level, there's going to be a file system that's being asked to perform a directory listing. And so that file system is going to read the file allocation tables and read file names out of those and return them. And then at a higher level in the application, there's going to be something just parsing that list and looking for something. So the check that I want to actually inspect isn't visible to me. That's actually in the processor that I don't have access to yet. So I think what I'm going to have to do, well, the first idea that comes to mind basically is to make an SD card emulator that returns basically just, every possible Well, there's a lot of ways I could do it, but one way I imagine doing it is I reset it, and each time I increment one character of the file name, and then I'm looking for a power trace where that comparison gets a little bit longer, like it made it a little bit further before giving up. And that's going to be really difficult to observe, but it is beneficial that this happened so soon after reset, because it's going to be much, much faster for me to run these experiments than the previous experiments I'd been working on. So it's basically like if you've seen any of the kind of examples for using side channel analysis to guess the combination to a combination lock. It's basically the same procedure, where the combination is the file name, and the guesses are files that we're placing in the file allocation table. And US Water Rockets again in chat asks, the SD card is not fat. No, the SD card is fat, but the card itself has no idea. Like, you're not asking the card for files, you're asking the card for blocks, and then the blocks have file listings in them. So all I can do is provide blocks that have files in them, and then watch and see how they're used. Anyway, this is basically what I want. Actually, the pins on the socket are pretty easy to access with the meter, so I think I want the socket pin out. Oops. I thought this would be easier to find. Is it just this pin? I think that's what I wanted, actually. The first hit, if I would just pay attention to it. So, yeah. This is certainly a different socket than I have. Just checking out the orientation. Anyway, I think I'm just going to stick a meter into this. Let's see, I also had this. And of course. So I think actually I want to label this image, just mark up which test points are which. So let's open that in an actual image editor. Oh, where is the title bar? How did the title bar become 1 pixel? Okay, fine. Oh geez, the Photoshop toolbars are on the other monitor. Okay, so something like that. Let's get those reference images too. Tuco, I hear you, buddy. Oh man, the spring release mechanism on this one is really different from the image here, so it's just confusing me as far as the orientation, but I think I'm just going to see which one is ground to check. So we should see ground on pin 6. And I'm going to assume ground is where all these capacitors are connected, and the ground plane. Oh, it would help if the meter was on. Hey Tuco, I hear you. I hear you a lot, little cat. That's pin 6. Okay, so I have them in left to right order. Grand. So that one's obviously ground. Let's just try getting our hex tool ready for that. Oh, all my toolbars are on the other monitor. Oh, that's not what I wanted either. Cool. Let's check this one. That's pin 8. Oh, this is really not the right size or anything. I'll just put the number on there. Where is that even going? One of these is going to be the insert switch. Maybe that's what's confusing me. That doesn't seem to be connected to anything except a capacitor, which I assume it's going to something. Let's come back to that one. That was This one right here. Let's try this one. Pin 3, which is command. And pin 2. Just got that one in the middle. That's pin 5, which is clock. Is 7.0. Oh, let me double check I had the right one. Yeah. That is this one. Pin 1. Cool. Pin 2. And this is probably power. For VDD. So this is probably the insert switch. Just trying to figure out where that goes. Maybe that's this little pad here. I think so. Does that just short to ground when I put a card in? Yes. Cool. Oh, come on. Whoops. Okay. So, let's It's like one of those cases where it would be nice just to have like super long 2mm headers. I don't think I would even need to make an adapter, but as it is, it might be easiest just to solder or to put another header on top of this so that I can have the logic analyzer and the card attached. All right. Need like a 9-position header. Will that even fit on here? I don't know, it's tempting to find some kind of 2mm header thing that I could plug into there, but I don't think I have the parts to make such a beast. So, it'll be something roughly like that. Bucket of headers. Let's see if I can have a 10-position header just to give myself some extra grounds. I don't know, maybe I'll use something dual row. I could try to mirror the layout of this bottom header just to try to maintain some consistency for whatever that means. So that'd be a 2x5. Oh, and recently Mike was reminding me to use UV cured glues for tacking wires down. I wonder if that would work for a quick header too. It might be worth an experiment. UV cured glues. And some way of clamping this. Basically like that. All right. Tiger. Oh, the automatic cat camera is going to be quite nice. Let's test this on something smaller first. Let's just see if I can glue 2 headers together. Make a DIY dual row and see how strong it is. Let's put this aside. Oops. That is not an entire vise. So, I mean, the tricky part with opaque materials is that the glue is only going to cure where the light can get in. So, don't know how great this is going to be, but I think that there will be enough exposed area that it could work out. Oh, Tuco brought me a bolt. That little cat is so thoughtful, always bringing me nylon. I think this needs to just be more central in the vise, which is just harder to get it in there. Maybe not the perfect vise for this particular endeavor. Okay. So this is the stuff I'm currently using. Just going to try a small amount right in between the two. Oh, this stuff is actually kind of thick. Hence the medium viscosity. Just try to smear it in between these. That might just be way too much. That's embarrassing. Should really be spreading this with something more effective. This stuff pretty much just will not cure unless you apply UV light. It does cure eventually in sunlight, but not very fast, whereas it only takes in the neighborhood of seconds to cure with a light like this usually. Let's see what that does. That is not strong. I might have just not given it enough time. It's not nothing, but it's certainly not strong. Let's give that some more time under the UV. I don't think that's quite lined up as well as it could be. Maybe I'll use the epoxy for this project. I think the 5-minute epoxy, at least I'm used to that stuff. Yeah, that's kinda working, but it doesn't cure very well right next to the surface where the plastic is blocking so much of the light. So I think I'm going to use a different method for this next project. Let's just use the good old 5-minute epoxy, probably. The other thing I could do is just solder it to the ground plane. Actually, I'm noticing if I do want to follow the, well, if I want a pinout that's actually just a mirror image of this pinout, then I could solder, so for example, these two corner pins are both ground, and if I, for example, had these two corner pins, which, I know those don't exactly correspond with this connector, because that would actually be the ones closest to me, not the ones farthest. That would still be a relatively sturdy way of attaching that connector. Let's try that. That's kind of nicer than the epoxy, I think. So, with that, let's take the memory card out and just grab it by this little stalk. So I want to put this pretty much right there. Oh. Looks like the Siemens here is also printed in copper. Or maybe I'm imagining that. No, the whole thing is copper fill. That's just the texture of the silk screen against the knife. Better access to the microscope in a sec. A little too up. That just barely reaches. That's a bad sound. Poor ball bearings. Okay. Okay. Let's just do some wiring now. I think my magnet wire is on the other desk. I'll be right back. Go back to the 32 gauge for a bit. That 40 gauge is just annoyingly small for most things. Let's have some pieces of those. Oh, where does that detect go? I'm tempted to put the detection pin next to a ground so that I can use a shorting jumper to fake the card being inserted even if it isn't. Oops. Check where that goes because it's not obvious from the diagram. That is... This one is card detect. And I'm assuming it's like... Ooh, is it that one? Oh, perfect. Yeah, so then if I make that correspond with this one on the underside, just to kind of keep the pinouts consistent, then that'll be my detect, and I can just put a shorting jumper. In fact, I'll put one of those on right now. And that'll be my card detect. And then we should see it try to talk to a card even when we don't have one inserted. We can start trying to simulate that in an FPGA whenever that becomes convenient. So... I think I want like all these test points. Oh, I should switch to the small soldering iron. Micro soldering. Yay. What's that goober doing on my solder? I think that was hot glue. I don't need that extra ground pad, but I'll take all the others. Yes, yes, multimeter. I get it. Giant booger. is definitely starting to get cold again. I used to live in a place that was actually kind of cold, like with snow and everything, but I'm not really used to that anymore. I've come to like my warm climate. That is too much booger. Oh, geez, look at how gross that is. Grunk. Let's pick that up. Oh man, this project sure has taken an unexpected turn. I did not expect at this stage to be thinking about SD card emulation, but that totally could be the next thing. So basically the point I'm at right now is I had everything set up to do exactly the glitching experiment that I wanted, and I had optimized, I was trying to optimize the time that the experiment took to run by speeding up the clock during boot and then slowing it down right before running the experiment. And that was all working nicely. And then I had it running for just a couple hours and it kind of bricked the PLC. And now it's in this state where it turns on and seems to be kind of alive, but also kind of not. Like, I've been looking for signs of life, basically trying to catalog, well, what works at this point. And so like you turn it on and it does initialize the LCD. So, and it's not just a power thing. Like, it could just be, at first I thought like, oh, it's the reset line is also triggering something else on the board to initialize the LCD controller. But no, it is actually their firmware initializing the LCD over like a parallel bus. So that's happening. But the thing I was hoping to find was some activity on the external SPI buses where I figured I might have corrupted some of the external memory, and then I could both fix the corruption and perhaps catalog it for use later. And my hopes there have been dashed. So far, I have not seen any communication on SPI before it crashes. It's not great, but it'll do. So yeah, there's like a glitch on I2C and no actual packets and nothing on SPI. So far, I was starting to come up empty. I was surprised to see the traffic on the LCD, which seemed to correspond with the largest part of the power waveform that I was seeing right after reset. So it seemed like, I was doing some boot up stuff, probably initializing hardware and libraries, and then starting to initialize the LCD. But then shortly after that, something crashes, and it just gets stuck in some kind of infinite loop. And it has not read any of the external memory at this point, so it has to be something that is getting stuck based on presumably some state in the internal memory. So now that I've discovered that it's also trying to communicate with the SD card, so with the knowledge that this is trying to talk to the SD card, it seems like maybe what I've hit upon is some kind of bootloader, and not TI's ROM bootloader probably, but probably something specific to this PLC that's looking for a file on the SD card. So that would mean maybe switching tactics, and instead of looking for a way to dump the firmware over Ethernet, maybe look for a way to actually bootstrap. And so, I don't know, there's a possibility that I no longer have the ability to get firmware out of this device, but I suspect that maybe I just set some kind of error flag causing it to go back into bootloader mode. Like, it seems unlikely that a single glitch would just erase flash memory, since it takes many steps for that to happen. It isn't something that could usually happen by accident. Somebody in chat thinks that micro soldering is a contest. I never claimed these were little, just that I wanted to use the littler soldering iron. I mean, they were really nice enough to bring all these out to test points. Don't have to solder any of these to actual IC pins or nothing. All right. I think that's all of them. Let's get the other ends taken care of. All right, so that's going to go continuing this kind of mirror image theme. For a while I had basically a micro soldering brag photo that I would bring up anytime I needed to, do my part in a pissing contest somewhere. My favorite one at the time was something where I was interposing on a memory bus between two processors, or a processor and its RAM, both which were BGA. And so I needed to get a bunch of signals, most of which were just available as traces or vias. Some of the traces were pretty annoying, and I had to work in a really tight gap. But the thing that I enjoyed showing off was this thing where I severed the chip select so that I could override it easily by excavating a buried trace and then separating the trace from a via and connecting to both sides of it on an interior layer and then bringing that out. That would probably be a lot easier now that I have better tools. But at the time, I don't think I had the 40 gauge magnet wire. So I was using individual strands from a piece of stranded wire. I think that's the next one that I want. Let me double check that. This one, I want to go kind of over there. Trains. Oh, Deadbug Engineering in chat asks what tools I used to get to the inner layer. A Dremel? No, a Dremel would have been way too big. I just used an X-Acto knife and kind of dug away the layers by hand under the microscope. Because I only needed to get a very small place. I think I had identified a via that had the signal, but I needed to, and it wasn't I don't think it was a completely blind via, so I had access to the top side, but in order to separate the chip select, I needed to actually separate a trace from it. So I knew that what I was looking for was going to be around that via, so I just had to start there and go down. And so it was through a couple of polygon fills on some internal layer. I don't know, it wasn't that bad. It was just, like, the hardest part actually was attaching to it because, or attaching to that little stub of a trace that I was left with. Since the surface tension just really did not want to let the solder stick to that at all. Not the best visibility into that joint. I think that's what's on there. This is not the prettiest wiring so far. So if we're going down that row, this would be the next one. Wants to go to this row. Ah, these are kind of dull. Oh. Can't tell if the recorder for this is stopped or... There are too many things to fit on the VFD now. There's one line telling me the audio recorder is low on disk space that's taking up a lot of room. I guess I should fix the disk space on the audio recorder. I don't know why I'm like leaning as if I'll get a better view due to parallax. Let's not have a giant glob of stuff there. Okay, next. Is that one? That one might be a no connect actually. Let's ignore that one. Or unless it's, is it this one? Yes, okay. Ah, there's too much junk on my table. Oh man, I'm still pretty stoked by how much better of a signal I was getting with a local amplifier on vCore. That was pretty rad. Like, the passive probe was doing pretty well for a passive probe, but definitely helps to have a 30 dB of boost right there. Oh man, you can tell how blunt these are under the microscope. Oh man, Tuco's playing with boxes. I gotta move the camera to catch this. Oh my god. just lose? Huh. Oh, cat. Tuco, do you want help? I don't think he does. If I were him, I wouldn't want help. I'll have to check to see if there are any existing HDL cores for emulating SD cards. It seems like the kind of thing that might already exist, but it also seems like the kind of thing that would be fun to write, and would also really, really depend on what you wanted the emulated SD card to do. And so maybe it's the sort of thing where writing a little state machine in Verilog is the solution I want. It was really satisfying using an FPGA to solve my triggering problem and just write a little state machine to do exactly the trigger logic I wanted. Honk. Ah, the great migration call of the West Coast oil train. Or maybe that's a passenger train, I don't know. There are passenger trains and there are cargo trains, and one of the most common cargo trains I see around here seem to be carrying like huge loads of ethanol. All right, top row time. This one goes to that third pin, where it pretty much already is, which is convenient. A while back I had to emulate an SPI EEPROM for some Nintendo DS hacks, and that was fun. I got to back it by SRAM that I could read and write over a serial port, so it was effectively like a memory chip with a built-in debugger. A collection of stuff like that seems like a generally useful kind of hardware engineer's toolbox. Just like a little doodad for emulating stuff. I mean, I feel like the protocols just end up being so specialized that the devices have to be kind of unique. I mean, it's easier to make a thing that like acts as an initiator to speak a bunch of different protocols than to make something which knows how to emulate a bunch of protocols. That pretty much requires like either an FPGA or some other kind of programmable state machine or programmable high-speed processor of some sort. So like an FPGA or maybe a propeller or an X core or something like that. Which pin does this one go to? That pin goes to the multimeter is off. Good morning, multimeter. That one, okay. Oh, Fedora in chat asks if the trains make more sound at night. I don't know, they make sound a lot. Maybe they're more noticeable at night because not as much else is happening. Because during the day, you also have sounds from the loading docks and people running their air compressors and other factory and shop equipment nearby. I hear you, cat. Do you want a thing, Tuco? You are sitting right next to me. You are not in the cat cam. 3. Oh, let's bring the cat cam back over here. Oh, do you just want food, Tuco? I think Tuco wants food. You want something to eat, Tuco? Looking for food, little cat? Just a sec. I'm watching what's on. Oh, that's what he wanted. Brr. Oh, maybe I should turn on the heater. Oh yeah, Deadbug Engineering in chat mentions FPGAs are so awesome. Being able to change hardware without touching actual hardware is so nice. I agree. FPGAs are a lot of fun. And as much as I enjoy building stuff out of actual hardware, it is really nice to be able to scale that up and, you know, make much more interesting things out of FPGAs than I've ever had the patience to do out of logic gates. This is the bottom pin. And that one is the second from bottom. Cool. Oh, and US Water Rockets mentions, did I hear correctly that Microchip has some PIC micros with tiny FPGA logic you can program via registers? That would be cool. I've not heard about that, but that would be pretty cool. Well, it'll be nice to figure out what modes and what commands are being used to figure out how much of an emulation we need. I'd be surprised if it uses all 4 bits of the data bus. Like, microcontrollers typically use cards in SPI mode because it's easier and takes less I/O, but they did bring out all 4 of the pins, at least as far as this board goes. So, and I think that this microcontroller has a peripheral which might speed up SPI card, SD card access. I mean, it definitely has an SPI engine that can handle 4-bit parallel. So I think that's what they might have been using here. But I haven't really looked into that yet. We'll find out shortly. All right, I think that's all the pins. So, I think what I want right now is, well, it's a little bent. Don't mind me just changing the angles on my plastic. Okay. So, got this contraption. Cool. So, plug that into the logic. None of this stuff should be necessary. ground to choose from. Then let's have clock. Then command, I guess. And 3 data, or 4 data. D0. D1 is way up there. D2. These, I think, are in order. That would make sense. D3. Yep. That's sensible looking. So we've got ground over here, and clock command, 4-bit data bus. I have this shunt on detect, so it'll always detect a card, but I'm also going to put in an actual SD card so we can watch it communicate. All right, let's bring this microscope up out of the way. Oh yeah, QSPI, that's the peripheral, as Kyle mentions, that they would probably be using. But, yeah. I mean, they're probably using somebody's off-the-shelf driver that would have implemented that, even if that's not what they need specifically. All right, this is unplugged. Let's jauntily plug that in. All right. Power. Using about the right amount of current, but otherwise looks as dead as we expect it to be. The LCD is turning on, but not much else. So let's get back on the computer that has reset control. Oh, I was misplacing the remote. There it is. All right. All right, you can see it reboot. Collects a couple megabytes of data every time I do that. All right. So let's put some names on these. In fact, we can turn off these two. Oh, thanks. All right, that's what we're looking for. So I think this was clock, command, and then D0 through D3. Can I really not tab between these? Oh, there's a question from Mark in chat. Is that a piece of lasered plywood you're using as a substrate there, Micah? Yes, it is. It's actually part of, this used to be the base for a spindle holder on my old MakerBot. I still have that MakerBot in somewhat working, somewhat in need of repair state, but I ended up disassembling the spindle box for parts since it wasn't really a great design, it turns out. Well, it does look like this is mostly staying in 1-bit mode, which is handy. forget how this protocol actually works, but guess I'm going to have to remember that very shortly. It's the command data. Let's see if there are any relevant analyzers here. Why did that show up as an empty window? Isn't that weird? Alright. I think MDIO might help. Is that the protocol we're looking for? I don't think that's quite right. Yeah, I don't think that's the protocol we're looking for. Sorry, guys. Let's just try SPI. Oh, I just want command, data, clock, no enable. Okay. Let's see if we can actually see any file system reads happening. Tuco's back in his spot on the keyboard. Oh, let's decode this differently. Yeah, this would probably make more sense if I had more of this protocol memorized. But I'm going to need to refresh myself on this. I did not expect to be going here today. I know a while ago the specs were hard to get. I think I might have found a copy. It'd be really nice to just get a dump of what this packet has in it. Save this. Analyzers, export. As text? Sure. Let's see what this looks like. Oops. Just looking for some headers I recognize, basically. This might be a file allocation table. Because I would expect it when it mounts the SD card to start reading the file system headers, and a lot of that's going to be empty, but you should see some telltale signs of like fat headers and maybe even like MBR bits. Actually, speaking of MBR, no. Yeah, I don't know. I think I need a bigger lever for this. Need more decoding capability. This should be a real card. Yeah, US Water Rockets was asking, am I talking to a real card or an empty socket? And I mean, we should be able to see the difference in the power trace. That might be an interesting experiment to do real quick. Let's trigger on reset. Oh, can we get this on that scope too? At least clock, maybe. Let's add another grabber for that, maybe. Just have some reference for when it's talking to the SD card. I'm going to get the scope hooked up with clock as well. Which I think I'm going to tap off of this black wire. Oh man, maybe clock is not the convenient one to grab. Command, maybe? That's a little easier to grab. Okay, hopefully not shorting that out on anything. That is 5. Okay, let's run that again. Really? No? It's a lot of talking. That's not right. Am I having a ground problem, perhaps? Because that looks like it's toggling consistently, or constantly. Let me get a logic trace to see what the Salia thinks about this. Yeah, the Salia shows what I would expect, where that is not toggling. D5. I'm going to assume I just have a bad connection. Oh, I can hear my youngest neighbor playing in the hallway. That's better. Okay, I think I got a better connection there. Interesting. Is that squicking out a packet during reset? That's interesting. Is that at all consistent with what I'm seeing in the Salia? I mean, I'm not getting the reset. I guess I should just put the reset on the Salia too so I can see that, but this doesn't make any sense. I don't know why I would be getting clock edges on there during reset unless it's just floating and this logic analyzer is picking up noise. That must be what's going on. It must just be floating. Let's try this again. So if the microcontroller isn't actually driving that pin as an output, it's just going to be picking up clock noise and stuff from nearby signals. So I'm going to assume that's undriven at that point. And then this burst later on is the one that I'm seeing on the Celia logic. And that corresponds with that little burst of CPU activity there. Now if I'm going to take off my jumper and then also take out the SD card. So with the SD card removed, nothing. With the jumper on, but the SD card not in there, we should see a shorter burst as it fails to talk to the card. If I can get the jumper back on. Ooh, or a longer burst as it fails. That's amusing. Is it going to fail forever? Does it ever stop failing? I guess it eventually stops, but it definitely fails for a while, like a second. Huh. Interesting. Probably not useful, but the more you know. Ah. So that's the condition with a readable card. And just for another reference, card removed, but the jumper still present. And then at the same time scale, I would like a trace without the jumper. Easier said than done. There we go. Okay, so it looks like that this kind of long wake-up period here is not necessarily related to the SD card. That could just be something else that's going on. And then returns to being relatively idle. All right, I think the next stage here is to have kind of a trace and injection rig for the micro SD card. So I think I need to go read up on the relevant specifications, since it's been a while since I've dealt with this, and I don't think I've ever done the quad pin version, which I don't think is what they're using here, but I mean, there's something going on D3. This might just be incidental. So you can see there's definitely the clock and command and D0 buses happening. This honestly looks to me like SPI mode, though. Like, I think this is chip select, and I think this is being used as data. And this is probably just not being used, or being used as like a reset or something. I forget how the SPI mode works. Let's try just decoding it using D0 as a chip select. And command. All right, just that. Not decoding. That's not acting like an enable, is it? I think that's something a little more unusual. Also, US Water Rockets in chat mentions that the card has to start in SPI mode for MMC compatibility. And yeah, that's what I'm expecting. But, so I guess this is the mode switch we're seeing. So this is what I was saying looked like SPI, but it doesn't actually seem to be totally SPI. And this right here is the very beginning. Like, this is what's happening right after boot. We've got a bunch of clocks with the data bus high, some more clocks, and maybe it's using D3 as a chip select, and this is data. Maybe that's how the SPI protocol works in this, but then it starts using D0 pretty soon after that, so like, I forget what order things happen in, but it's going to be switching from protocol to protocol until it ends up somewhere. And then down here, it seems to start doing something different with D0. How fast is this clock? 8 megahertz? And that's with this thing running at close to 100% clock rate. So I could slow that down if I wanted to, but it would boot faster if I could operate at this clock rate. Yeah. So just as an update for where we are, yeah, the device is still semi-bricked. I've exhausted some possibilities, so I know it's not talking to any of the other onboard memories. I think this means that I must have somehow set a flag either in the onboard flash or the onboard EEPROM that causes it to execute differently. I'm hoping I didn't actually just like erase the firmware, but I think that would be difficult to do. And so at this point, you know, it's still kind of bricked. I'm just looking for things that are alive, and I found the micro SD card slot. And so it looks like it's in some kind of bootloader mode where it's at least looking for an SD card with maybe some files on it. So I think the next step here is to build a little SD card emulator so I can just quickly reboot this thing and keep feeding it generated SD card blocks and looking at the power trace in order to figure out which ones, you know, which file names, for example, would cause interesting behaviors, which is probably going to be relatively straightforward once I get the infrastructure set up, but it's going to require some infrastructure changes since I'll need the way to emulate the SD card, and I'll need to kind of retarget the power analysis I'm doing to that portion of the system. But yeah, not totally bricked. It's, you know, it's probably still got its firmware. It's got at least the bootloader, which, you know, one way I could imagine this going is we just sort of figure out how to wiggle our way into the bootloader and maybe give it a file that it starts to process. And then maybe that file has a straightforward format and we can figure out how to load a little bit of code into Flash, maybe without overwriting much of the firmware and then read the rest of it back. Maybe we can figure out how to get the bootloader to do something interesting while parsing the file system or something else and get code control there. There's a lot of possibilities here. But yeah, I think the first thing that needs to happen is I just need to go refamiliarize myself with all of these protocols and see if there's any existing emulators that I can repurpose or if I'm starting from scratch here. We've got a bunch of this. I was hoping to at least see like some file system-y stuff in here, but I think that might be happening in a protocol that's tedious to decode this way. But honestly, I don't know. Like, if it was reading fat tables, I would expect that to take more time than this. I mean, we could try decoding this different ways. I mean, in this protocol here at the end, it certainly looks like command is acting as a chip select, and D0 is the only relevant data. Let's see what it looks like if we decode it that way. Hello, decoder. This decoder also doesn't seem to like it when the protocol is not valid in the past. Because I think it just decodes from the beginning to the end instead of trying to decode what you're looking at first. So this might just be annoying. Oh, it's a good suggestion to fill the whole SD card with dead beef. I don't think it would be reading the whole SD card, though. Like, I suspect it's actually just reading a very small amount of information. But that is a good point, that I don't even know if this SD card is formatted. So, like, yeah, let's try putting at least some files on here just to see if we can see it. I mean, that's what I was looking for. I was looking for it reading like a file allocation table or a directory entry. Where's the closest SD card reader? Is it under the cat? I think it's over here somewhere. Tuco, are you stealing my seat? Oh my god, Tuke, you're such a jerk. Fine. You know that one's not going to be warmer than the laptop. Unless I put it next to the heater. Is that what you want? Do you want to go back next to the heater? Getting back into this old tradition. Oh, cat. Oh, Tuco turned on voiceover on my laptop. Station 250 in chat wonders if it's worth trying some common file names like rom.bin and stuff like that. I could try to brute force it, but I feel like that's probably gonna, like, I don't know that that's gonna do much unless I have at least a starting point. And if I knew that this was based on some kind of other bootloader, then, I mean, yeah, I mean, I could see it being like update.bin or something like that, but I think it's maybe a little premature to just start guessing file names. I think I want to have, like, I think I'm going to need some kind of framework for quickly testing a lot of different stuff before I start testing a lot of different stuff. Hello, USB. Is the cat happy? The cat is in cleaning mode. Oh. That's the right one. Well, it was already FAT32 formatted. Let's try formatting it again. Is this not... That's interesting. Is it going to give me a FAT16? Invalid argument, huh? Is it just, was that just a transitory error caused by having an empty directory? That's weird. So let's just make a bunch of file names. Just make 1,000 files. Is there an os.touch? No. Just make some files. Just making files, making lots of files. Oh, or making a lot of the same file because I forgot to put the substitution in there. Thanks, me. That's what I wanted. Okay, let's save that. And new capture. Ooh, this looks longer. Good call. I think we're getting a lot more directory entries now. Let's make sure we're comparing these at the right timescales. That one is irrelevant. This one is, wow, yeah. So we're looking at both of, geez, yeah, that's even, that's the same time scale, I think. 10 milliseconds. So let's see, it starts out a bunch of the same, mostly zeros, but something that's presumably initialization and mode switch related. A lot of that happening. Some reinitialization maybe? And then talking to it in a different mode. These look like bytes in 1-bit mode. And then maybe this is it actually reading. It does still seem to be 1-bit. Can we decode any of this? The SPI decoder is not having a fun time here. I don't think it's decoding that correctly. I think it just gets confused way back here and then stops. Or maybe I have the polarity wrong on the enable. Oh, Kyle has a good suggestion of checking to see if any of the UART pins have suddenly started being UARTs in the new mode. I did check to see if any of them have outputs, but I hadn't tried just like spewing data into them. But yeah, I do suspect that, you know, if I were Siemens designing a bootloader for this thing, I would want, well, I definitely want to be able to load code over the SD card. I think they also make some kind of dongle that plugs into this port and gives you a serial adapter. Like, I've seen references to this, but I don't know how you buy one. I haven't found any binaries that talk to it or anything that's more concrete like that, but just some reference to a serial cable that might exist. And I suspect it might just have like a pass-through for the RX and then like an SPI to asynchronous converter for the TX of some sort. This is looking data-like. It's too bad my decoder doesn't decode. Oh, maybe... Let's try this. Active high. I think that was the problem. Yeah. Let's export this again and see if we can see file names. Yeah, file names, foo106.txt, foo105.txt. Yay. Well, cool. I guess we just have to implement 1-bit mode or whatever combination of 1-bit modes they're using. I need to figure out what this actually means as far as the spec is concerned. But Yeah, I think the next step here is emulating something that can at least handle initialization and reading disk blocks. And then basically I want to run tests where I generate directory tables and then try to get it further along in making decisions based on the directory listing it reads back. Oh, Mark in chat has an interesting hint. eBay, I think he has a listing, they have a listing for an RS-232 card. Sodium asks, could I just write all the files to the SD card? I don't think that's possible. Like, if I just wanted to enumerate all the 8-character file names, I think that's still larger than the file, like the fat directory can hold. I think at some point you run into limitations as to how many files can be in a directory. And then I guess there's a flip side of that. Like, could you just keep, like if you're emulating this SD card, can you just keep returning file names as much as you want? I don't know if that would be valuable, since I suspect what's going on here is, I don't know, there's a lot of different ways this could be implemented, but that wouldn't work if, for example, they were reading all the file names into memory and then figuring out what to do, but like, I didn't see significant gaps in the logic trace. So like, it doesn't look like they're, you know, reading some directory entries and then making some decisions and then reading some directory entries. I mean, maybe that's what these gaps are. That's 1.8 milliseconds. So I mean, I guess one way that this could be going is these are the gaps where the file system code isn't, oh, that isn't an actual gap. That's just a bunch of zeros. Never mind. Yeah, I don't see any gaps. Just, these are 30 microseconds, which does not seem like, it's just like an intertransaction delay, not necessarily like the code getting some work done. So it looks to me like some relatively low-level part of this program is just bulk reading the entire file allocation table. Oh, that's a good suggestion too. In conjunction with the timing and power side channel, you might have file names that help you narrow down the file it's looking for without writing the emulator. That's also certainly true. Like, I was imagining doing the kind of steps kind of automatically, but I could certainly just write a bunch of, like, you know, A, B, C, D, etc., and then try to get a sense for which of those is causing it to make more progress. But yeah, for any of that, I need to get a better sense for where the actual comparisons are happening in the firmware. So maybe let's go back to the O-scope. We want the reset button. Are we not having a scope? Oh, we are. It's just very slow mode right now. Yeah. So that's the same kind of single lump of transaction-y kind of stuff that we saw before. And I guess one thing to do is to try you know, I think one experiment to try quickly is actually to have two SD cards that are the same, other than one of them having a bunch of files in it and the other one being empty, and then just swap between them and see if I can identify where the difference in the power trace is. I think I have more of these same 8 gig SD cards. I'm gonna have some SD card spec bedtime stories for myself in the near future. I'm sure it'll all start coming back. All the weird commands that were very sparsely documented last time I looked at that. Keep your memories safe. No, no, let's actually do the opposite of that and format this disk. All right, let's just leave this one empty, but formatted. Come on, eject. You can do it, eject. Oh yeah, US water rockets suggest you could really try all the files, emulate an SD card with one file and increment it each time until it behaves differently. Yeah, that was pretty much my original plan. Like, write an SD card emulator, then have it reset, and every time it goes through, increment the file name, and then look for a trace that indicates it's hit a match, and then move on to the next character. Why is this not ejecting? But yeah, there might be ways to get through this without even having to write the SD card emulator. But I would still like to do some research to see if one already exists. I guess it was ejected. I don't see it in Finder. Oh. It would be certainly nice to have such a thing. I've often wanted an SD card emulator just for, just for day-to-day use, as you do. Okay, let's try to get a comparison of these on the scope. So just to make sure, that's what we have from a bunch of files. Is that tracing? That gave me 2. Come on. Okay. Make sure that we get a really nice zoomed out view, because I want to mark the end of that kind of thick power trace where it's processing a bunch of stuff. And then I also want, I want to mark the end of the communications trace. Okay. I can see which of these are related, potentially. So let's just make sure those stay stable if I do another trace. This takes a while because that's 1 second per division. Did it not trigger? Okay, scope is triggered. That's pretty stable. Okay, switch SD cards. Man, it's just so weird to even think about the mechanism by which I bricked this thing. I mean, all I was doing was voltage glitching it, just causing it to run incorrectly. Triggered. Come on. Was that it? Let's give it another shot. I think what happened was the communication got a little smaller, but the other one stayed put. In which case, I think we should zoom in and get a closer look. Yeah. So I think that trigger where X2 is, I think I'm going to ignore that. That's just something else where, like, I guess after the bootloader makes a decision about what to do, it's waiting for a while, or possibly that's it getting stuck. That's interesting. I don't know what that tail signifies before it goes back to idle, but it doesn't seem to be related to the file allocation table. So this should give us a closer view. Hello? Oh, there we go. Okay, that's better. And this is going to benefit from some kind of fast switching setup if I end up doing this a lot, which I hopefully won't. So definitely a lot more activity during the communication. I don't know what processing it would be doing during that versus after it gets the data. No, it's pretty stable. Oh, cool. You can see little bursts of processing when it handles each SPI interrupt. That's what we're looking for. So that, not that. Oh, now we're starting to get into jitter territory. We need a better trigger. Yeah, this needs a much better trigger, because this is still triggering just off the reset signal. Oh yeah, this would be really nice to actually have the power and the data on the scope at the same time. So we are seeing some interesting processing there. We trigger on D5 at this point. Oh, maybe with some hold off. Oh, I don't remember how to set the trigger. I don't actually know how to set the trigger hold off on this scope. Here we go. Now it's triggering on the glitch where anyway, I definitely need a better triggering system in the FPGA, even if I don't have to emulate. I think I want something that can trigger. But yeah, I bet I could get I don't know. I think right now I feel like I need to read some documentation since I'm operating with less information than I'd like about these protocols. But I think maybe the next step is probably just to get more of this on the scope and try to get a sense with the power analysis and and the data trace up there just to get an idea of how this bootloader is processing the SD card contents, and then try to see where we might look for changes. This power trace is all very fascinating. Oh yeah, I don't think I've actually showed the new amplifier on camera before. That's what we have to thank for a lot of this. Let's unplug this. Oh man, there's so much stuff attached to this. Not that button. Come on. That sort of did what it was supposed to. Oh man, this is such a mess. Let's... Oh, I need a helping hand thing that is on the other side of the room. I'll use a multimeter. That is my current bodge of a situation that actually seems to be going all right. So that's the location where there used to be some V-core capacitors on the board. So I took those off, replaced it with some of this twisted enamel wire. One of those going to my glitching board with its MOSFETs, and the other one going off to this little resistor network where I was trying to impedance match it as best I could. That is 100 ohms in series and 100 ohms to ground, so the amplifier sees 50 ohms at its input. And then the output just goes to a scope channel that's also 50 ohm terminated. And then the amp runs off the same 12 volts that goes to the glitch power supply. So that thing seems to be working all right. I did also make some B-field probes recently, just by basically taking these same amplifiers that are like, this is what, 30 dB? Yeah. It's a 30 dB amplifier rated for like 0.122 gigahertz. Or no, 0.1 megahertz to 2 gigahertz, sorry. So it's pretty broadband. And at first, I was kind of underwhelmed by it, but then I realized that the signal I was actually, that I thought I was looking at was actually a noise artifact from my test setup. And now this is letting me see much more into the power waveform than I was before. I think they were like $8 on eBay. Or no, I think it was like $8 for a pack of them. They were not expensive. Well, all right. Let's maybe... Let me get these on the other scope. Inconvenient to have these on the ciliate also. Oh, geez. This needs some glue. It is not super sturdy without glue. I just started to unplug these and the pins started moving around in their sockets. So I should keep this plugged in and add some super glue. Triggering. A lot of this is going to depend on when things are happening in the power waveform, but I mean, I would expect it to be happening pretty late. So if you're writing code for this, you're going to call some function that reads a bunch of stuff from the file system, and then it would presumably mostly hang out in cache. At least directory entries would hang out in some kind of temporary data structure, which you would then manipulate. It's really hard to get the glue on those bottom pins without also just getting it absolutely everywhere. But at least it won't come apart. Yeah, those little 3-pin amplifier chips are really cute. I'd seen them in catalogs, but I hadn't actually had a reason to use one until this project had me ordering breakout boards for them. All right, well, I'm thinking this might be a good wrap-up point for this stream, since I need to do some research and possibly make some more tools. And before I do much more with this, I should at least let the glue dry and maybe make some other like splitter rig so I can attach 2 logic analyzers to it. Oh man, I can see needing to split this like 3 ways to go to 2 logic analyzers and an emulator, but that's the way these go. Oh, maybe I can get those B-field probe out here. Let's see, this is one that I made for like low frequency stuff. I was actually working on this, and my friend was over, and she, well, so she's like an electronic musician, and we were both kind of curious about these sounds, and so, you know, we were listening to stuff using this probe, which is just a single loop of, basically took a piece of this coax, stripped it, bent this over, soldered it back to the shield to make a single turn loop of wire, and then encapsulated it in some plastic to make it more insulated and a little easier to hold. So this is good for the high frequency stuff I'd been using. This is like a 1 millihenry inductor with like probably hundreds of turns of wire. And so that'll have like way too much self-resonance to pick up high frequency stuff, but seems to pick up more of a signal in the audio range. And then in here I just have one of those same amplifiers, this time inside of a metal tin for a little more shielding. And I have the output just soldered to the tin, and the input is in here so that it's a little shielded. Yeah, very cheap solution. Let's tighten that. And I was just running it off of a 9-volt battery. And I need an SMA adapter for this. Not these. Not these. And one of these. BNC to SMA. All right, let's compare this with the V-core probe. Where's my trigger? Oh, it's way back there. Where's my trigger? It does not have anything to trigger off of right now. Fine. Alright, there's some power waveform. And this is on channel 4. 50 ohms. Ow, it didn't like that. That is sensitive. So that should mostly be getting the clock. What is that frequency? Yeah, that is, I forget which frequency that is. That's one of the frequencies that is relevant to this processor. I think that's twice the input clock. But yeah, let's maybe get something that's a little bit more coherent. Maybe synchronize this on reset again. So I don't currently have a good system for positioning this. Like, I can imagine having a nice like ring stand or some kind of positioner. Right now I just have a plastic thing. If this kind of probe works out nicely, I might try to make a nicer one that I can like position down on a little pole of some sort. Anyway, let's try getting something correlated with the reset again, which was D7, yeah. Oh yeah. So so far it hasn't been giving me as good of a signal as probing the V-core directly, but it's, you know, it's something I can work with for sure. I've already found it interesting just to see if there's something in there that I'm missing in the other signals. And that's totally non-contact, so you could do this on, you know, a running system without disturbing it. And let's see. Also get it picks up a really strong signal from the clock wires over here. Am I getting something from the SD card port? Not with the SD card not connected. Oh, that's probably the LCD's internal refresh. Because it's like the LCD itself has a switching power supply in it. Oh yeah. You get a lot of EMI off of cables, of course. So that's probably picking up one of the LCD power supplies via the flat flex cable. What is that? That's just clock again. Oh, or that might be the switching power supply. So this whole area over here is going to be switching power supply noise. And there's this picking up the CPU again a little bit. And try the chip whisperer. Bunch of stuff that's not correlated with this. Oh, a lot coming out of that chip, huh? And this is the other microcontroller up here. Oh yeah, definitely a good point from Kyle that I could use like a 3D printing bed for scanning. That's been one of my thoughts for what to do with. I've got an aging MakerBot that I've had kind of a tentative plan to restore, but it's like such a not so great printer that like you could get a much better printer for not much money now, and so I'd almost rather use it as a Cartesian robot for doing other experiments. So this is definitely one thing that I could try. Stick a B-field probe in there instead of a hot end, and stick the circuit board on the bed. So that would be great. But yeah, that would definitely be something to do for locating. Like it'd be really nice to have maybe a single probe head with a coil for like a single loop coil for sensing, and then maybe also some other kind of coil for fault injection. Or possibly you could even use the same ones, but that might be bad for the amplifier. Just try plugging this back in, maybe. Oh, still some super glue residue near that. It's going to be taking imperceptibly longer. Oh, actually, I had this probe, which fell off, so we can't actually see that on the scope now. All right. There we go. That is our... There we go. That is the actual point where it's communicating with the SD card. This is the one with lots of files. So that B-field probe, curious what we get on the SD card itself. Ooh. That's nice. Can we get more of that? I'm just playing with this probe at this point. I think for this circuit it's probably not giving me information that I can't already get via other means, but it's certainly interesting. And this is getting into the situation where there's probably too much jitter for me to be getting the trigger reliably. Where is... Oh, it's like behind everything else. There it is. Let's do... So there is like one fancy trigger option on the scope that might do what I want. There's like a trigger on one edge after you've seen a different edge. I think the weird edges on the SD card were happening... Yeah, they keep happening shortly after reset. It doesn't stop until... like 20 milliseconds after reset. So like what I really need is trigger... Like first... wait for this edge on D7, then wait 20 milliseconds, 25 milliseconds, no matter what, then look for an edge on D5. So I don't know if I can do that, but let's see. Edge, then edge. Oh, actually this delay might do exactly what I want. Okay, cool. So we arm on D7, trigger on D5, positive slope on both. Delay of 25 milliseconds. Oops. Oh, that's got to be from the beginning of that. That's right. I think actually I want the end of reset, not the beginning of reset. So let's have that be falling edge. Yay! That's the thing I wanted. Thanks, trigger. Neat. Probably get a cleaner signal out of that if did some bandpass filtering on it or something. And a lot of that's probably just the communication buses rather than any internal processing in the SD card. But if we filtered that out and then maybe had a probe that was actually closer physically to the chip, then we might get that kind of information out. That's all the noise that just comes from being in proximity of that region. Like over here, not much. Interesting. Would definitely be interesting to get a 3D map of it or something. Oh yeah. Yeah, Kyle's also mentioning using the EMI to get data out. Like if I, if I write some kind of test, that seems really interesting too. Yeah, because this is like GPIO debugging, but it works even if you have no idea where the GPIOs are on the system. Which, in this case, it's something we can work out, but it is a nice tool for delving into the unknown. Well, I think that's enough playing with the B field for today, but I'm sure it'll come back out at some point. Alright, I think it is time for me to nom on some more cold pizza and read some SD card protocol specs, since I would like to have a better idea of what I'm dealing with here to formulate my plan for attack. I think the plan is probably going to be something pretty straightforward in terms of either making a couple of sample SD cards that have test patterns on them, or making a really simple SD card emulator. It's looking like this might not be that hard to emulate, and I feel like I'll be especially emboldened if I read some more of the spec and discover just how little of this I actually need to implement for this device to make it this far. Since, yeah, I suspect this will actually end up needing a very small amount of SD card emulation to read the file allocation tables and do whatever subsequent processing it's going to do. One of the first things to look for is for sure going to be finding, where is our oracle in here? Like, where do we look to find kind of hidden information about whether it's finding a file that's interesting or whether it's getting close to finding a file that's interesting. So for that, it would help to understand at a high level, like, what does the flow of their SD card stack look like? Is it generally, at what level are things being buffered, basically? When is control going back and forth between the application and the driver? What I would expect to see is most of the processing happening after the whole thing's been read, but I didn't really see much going on there, so we might have to take a closer look at the earlier operations to get a sense for what's going on there, too. It's It's also possible it's happening later than we expect and it's kind of disappearing in that other large blob of a loop, but that seems less likely. So, oh, yeah. Yeah, definitely some interesting experiments ahead with plotting things in 3D with a CNC. I'm super interested in having like 3D control over a glitching apparatus that operates, using RF side channels. So that would be quite neat. But yeah, I think that's the thing today. We have discovered. Well, I was hoping to find a slightly easier solution out, but at least this is interesting. Like, this is leading into some interesting work on the SD card that I was probably going to want to do anyway, so that's pretty neat. And not as bricked as it could have been. So, here's the cat. Oh, nice. Kyle mentions that they could effectively clock glitch a platform with a PLL by slamming the PLL with RF. That sounds about right. That would be interesting. I haven't really gone into clock glitching on this one so far because it seems like the voltage glitching has been a more reliable way of generating a glitch at a particular time. But, I mean, for all I know, this particular bricking incident could have been caused by clock glitching, because my method for ramping the clock is very not sophisticated. In fact, we can take a quick look at that. Yeah, so here's my clock generator slash kitchen sink of triggering monstrosities that go into this setup. So it's got, let's see, so reset, that comes from the chip whisperer, goes to this and to a transistor that pulls the reset down on the target, but this one is active high. Input clock from the chip whisperer, 2 output clocks to the Ethernet and the device under test MCUs. Then this is for the triggering system. I have it getting that initial trigger from the Raspberry Pi. Then there's that signal we're generating on the PLC that just toggles every time we go through the main loop. We're sampling the Ethernet packets and then generating the trigger. So I've got this little state machine that's just looking for, so I'm buffering the inputs with a couple of flip-flops and detecting edges. And then this is the actual state machine. So first it waits for a trigger from the Raspberry Pi, then it counts 2,500 Ethernet packet edges, then it synchronizes to the next edge on that clock signal coming out of the PLC, and then it stays active until the Raspberry Pi shuts it back off. Clock divider, yeah, so the internal clock that this is using is about 135 megahertz. It's a ×5 PLL from the clock that the chip whisperer makes. And normally, my normal level of underclock here is a divide by 24 after that. And so the ×5 and then divide by 24 is the inverse of what the system on a chip here is doing. But if I divide by only about, well, in this case I chose 6 because I wanted an even number, but about 5, then I get back to about 100%. So this actually just slowly changes the divisor. And so I end up with these kind of big jumps as it moves from one frequency to the next, but hopefully those jumps aren't so bad that it totally locks up the PLL. And so far it seems to be mostly working, but I could see this causing some processor glitches that end up messing up memory. It is nice you can watch the, I can probably demo this. You can actually watch this work on the LEDs here. Oh. Yeah. So the LED in the middle indicates PLL lock, and the LEDs, the 4 outer LEDs are just a counter that shows you the clock is running. If I reset, you can see that momentarily the clock speeds up for a few seconds and then it goes back to normal. All the stuff that we're looking at with the SD card, though, is happening before the clock slows down, so none of that's going to be an issue yet. But to verify that, I was watching the toggle output from the PLC program speed up and slow down, and that was working fine. So that seemed to at least work all right. Oh yeah, also spark gap, that would be another idea. I did briefly experiment with RF fault injection using just like a small coil, like a few turns of wire, in series with a photo flash discharge tube and a capacitor. So basically just modified a camera flash, and that could definitely reset the processor from many inches away, so maybe a bit too strong of a glitch. Oh yeah, Kyle in chat asks if this chip has an internal PLL, and yes, it definitely does. It's the way it's normally configured, it has a 25 megahertz external crystal that runs the Ethernet peripheral and also serves as the input for the PLL that runs the processor at like 120 megahertz. So that's why I had to slow down the Ethernet, since I wanted the processor slowed down. They're both using the same 25 megahertz clock. Oh, yeah, and so Kyle mentions if I rapidly shift the clock frequency, the PLL would ring as it restabilizes, and that is probably happening. And yeah, I was trying to make the jumps not super big, but I mean, I know it's not the optimal solution by any stretch. It just, I didn't have a VCO spare to use for this. Yeah, the right way to do this would be to have like some kind of clock synthesizer that has a VCO that I can program to smoothly move to different frequencies. I just didn't have that on this setup, and it seemed like I could get away without it. But yeah, I'm sure I was causing some internal chaos more than I was otherwise, more than I necessarily needed to cause with the clock switching frequencies. I'm still a little baffled as to how I caused non-volatile memory to write, but lots of different ways that could have happened. I think at this point I just need to go hang out with some SD documentation. Oh, this might even be MMC. Like, I'll have to see which parts of the spec are even relevant, because it doesn't look like they're using an especially fancy mode. They're just using 1-bit. Yeah. All right. Well, thanks for tuning in, everyone. Thanks for hanging out and hacking hardware together. It's fun. Thanks for all the support in hardware and hugs and dollars. It's all been helpful. And thanks for hanging out with Tuco. Oh, yeah. Kyle, another theory from Kyle is that one peripheral is permafaulted, and that yeah, maybe I broke something in the startup sequence. Yeah, that would also be weird. I don't know how that would happen, but yeah, maybe some kind of latch up that broke something. So yeah, maybe if I did end up bricking this chip in some way, then when I try this on a fresh chip, I hang out with the I hook up the external VCO and set up that correctly. So anyway, lessons learned. Good night, everyone. Happy hacking.